Hello, calculus students. Welcome back for another video lesson. Today's lesson's focus is on the definite integral. So we're going to start with some definition and notation. If f of x is a function defined on a closed interval a to b, then the definite integral of f from a to b is given by this integral notation on the right, which is equal to the limit as n approaches infinity of this Riemann sum on, I think I should have said left, and the right. So basically we're going to understand that a bounded integral is equal to its related Riemann sum, if such a limit exists. In this notation, f is called an integrable function, and a and b are called the limits of integration. For an example, let's use the definition of the definite integral to evaluate the integral from 0 to 2 of x squared dx using a right endpoint approximation. So if we write it out with our definition, we're going to write 0 to 2 x squared dx equals the limit as n approaches infinity of the sum from I equals 1 to n. And this is where it gets a little ugly. So we've got this f of xi asterisk delta x. And so we need to define what each of these variables are going to mean. And I'm going to start with delta x. I know that delta x is the width of the partition, which should be the entire width of the interval divided by the number of subdivisions. In this problem, the interval goes from 0 to 2, so this is going to be 2 divided by n. And we're going to save that because we're going to need that later. So I'm going to go ahead and plug that in delta x's position so that I don't lose it. Next, we have this f of xi asterisk, and so we're going to kind of need to define what xi represents, and then we can define what f of xi represents. A right-hand approximation actually starts at the first partition. It doesn't start at 0 or x0, although in this case x0 is 0. So for this one, when we go to define xi, we're basically saying x0, or the very first x value in the boundary of the integral, plus our delta x. So if you're thinking about it and you've got your partitions, and let's say it does go 0 to 2, a left-hand sum is going to start at 0, but a right-hand sum is going to start at the very first delta x. And then because we're trying to represent every possible value of x in our sum, we need this I. So we're going to put an I on this, and then it's going to represent when I equals 1, I equals 2, I equals 3, all the way to infinity. So let's simplify this expression down. Xi, or the position of x after I increments, right, I 1, 2, 3, is going to be equal to 0, the beginning of our boundary, plus delta x, which is 2 over n, I. Well, in our equation, we need to put f of xi. So here's xi, and in our function, we have x squared, I believe. There it is. So over here, f of xi is going to be 2i over n squared. And then we're ready to continue with the evaluation. So let's simplify this expression. This is going to be the limit as n approaches infinity of the sum from I equals 1 to n, and then 2 squared is 4 times 2 is 8, I squared over n squared times n, which is n cubed. Now in this context, I is the variable defined in our sum, and n is really just a constant in the sum. It's not actually a constant in the limit. We know that n is going to go to infinity, but we can treat it like a constant for the purpose of evaluating the sum in terms of I. So we're going to pull out the 1 over n cubed as a coefficient, and just look, what is the limit as n approaches infinity of 1 over n cubed, right? This is going to be part of our solving. And then we just need to evaluate our sum with summation notation, which is something we reviewed, I think, 2 video lessons ago, but maybe it was just part 1 of the last video. Actually, I'm going to take out this 8 as well because I don't need it. So we've got 8 over n cubed on the outside, and then we're really just left with the sum of I squared. So think back to your notes or a previous lesson. There is a formula for the sum of these perfect squares, and we're going to substitute that formula in right here. And I'm just going to do it off to the side and then put it into my limit. So the formula for the perfect squares should be n plus 1, 2n plus 1 over 6. But you should double check that in your notes, and I'm going to be double checking that on my notes as well. So we know that this sum here, I'm going to highlight it in lime green, what can be replaced with this expression right here, because this expression will evaluate a sum of perfect squares up to a given n. That leaves us with a limit as n approaches infinity of 8 over n cubed times n plus 1 and 2n plus 1. And so this is a lot of algebra. We're actually going to go ahead and simplify this entire expression out so that it's a single polynomial with multiple terms. Pause the video here. The next thing I'm going to show is the final solution when all this algebra is worked out. So here we have the limit as n approaches infinity, and I'm going to leave the 8 over n cubed for my simplification, and then this expression is now 2n cubed plus 3n squared plus n all over 6, and it needs to be simplified. So I'm going to do a little erasing here on the side to give myself some more room, because it looks like I'm really running out. Although with a little bit more algebra, we should be good to go to evaluate our limit. So equal to, and I'm just going to put this up here, this is the limit as n approaches infinity, and then let's go ahead and distribute the 8 over n cubed to each term. Remember, each term independently is divided by 6, so I'm going to be simplifying out loud as I go. So this first term is 2n cubed over 6. The 2 and the 6 simplify, so it's really n cubed over 3 times 8 over n cubed. That means the n cubes are going to cancel, and all I'm left with is 8 over 3. Then we're going to distribute the 8n cubed over n cubed to the 3n squared over 6. The 3 and the 6 will simplify, so this is really n squared over 2. When you distribute it, you're left with 8n squared over 2n cubed, which fully simplifies to be 4 over n. And I do recommend you write this out and really show this scratch work, especially in your own notes. I'm just trying to save space in my video notes. Finally, we've got plus n, this is just regular n. So 8 over 6 reduces to 4/3, and n over n cubed is n squared. So we've got 4 over 3n squared. Now let's evaluate our limit. The 8/3 is not affected by an ever-increasing n value, but 4 over n is going to approach 0 as n approaches infinity, and 4 over 3n squared is going to approach 0 as n approaches positive infinity, which means that the area under this curve exactly is 8/3. And this is actually what your calculator is doing when you use your integral function and set the boundaries and get an exact answer. All right, we're going to let this be part 1 because this is kind of the big thing. And you know this is a lot of algebra. Yes, I'm going to teach you a shortcut in the next lesson, but just like we had to use the limit definition of a derivative when we first came up with derivatives, we really want to rely on this Riemann sum definition of an integral and make sure we understand this concept as well.